to finish up where we were on Friday. We were talking about the measure of an angle. We'll get through kind of categorizing some angles, which you already know, and then we'll set up the protractor postulate, and then we'll do an angle addition question. Okay, and then hopefully you got maybe a few minutes to put a dent in your homework tonight. I think we kind of mentioned, we briefly maybe discussed this on Friday, but then we went away from it. But there are two ways to talk about a measure of an angle. Okay, two types of units. The first unit, you guys are accustomed to, you're familiar with, is dealing with degrees. Okay, so if I were to write here that one technique is degrees. Now we're going to talk about 0 degrees to 180 degrees mostly. Okay. Towards the end of the year, we'll talk how that goes from 0 to 360. And then when you get into trigonometry, we'll talk about how that goes to 0 to infinity, and actually how it goes from negative infinity to positive infinity degrees. Okay. Those are aspects, but most of the time in geometry, we only focus on 0 to 180 using that terminology. And then we'll build on that into the end of the year and other courses. So you should be accustomed to that. Is anybody not comfortable with degrees? Okay. The other technique is what we refer to as radians. Okay. This will be something that you are 100% uncomfortable with and probably don't understand right now. Okay. And when I teach this to my trig students, it takes some time before they become really accustomed and comfortable with it. Okay? But radians is actually a more fundamental approach to measuring something than what degrees are in regards to an angle. Now, kind of talk about the idea here. You guys are very, very comfortable talking about miles, right? And understand what it feels like to go 20 miles an hour, 30 miles per hour, that kind of thing, because you're accustomed to that unit. If I ask you how fast are you going when you're going 28 kilometers per hour, you're not accustomed to that, right? You're not used to kilometers, because the kilometer probably wasn't introduced to you until maybe the 6th grade, 5th grade, and you'd already been spending 2 or 3 grades on miles and dealing with miles. So kilometer was a little bit of that abstract concept to it. Okay? Those of you that maybe run cross country or track, that kind of stuff, are probably a little bit more familiar with kilometers than anybody else is, right? Okay? But if you just run for fun or for exercise, most people know what it feels like to run a mile. If I ask you what's it feel like to run a kilometer, is it more difficult or less difficult than running a mile? That's less difficult. A kilometer is shorter than a mile, right? Okay? So when I ask you what's a radian, there's going to be a question there. So I want to show you what a radian actually is. Did we talk on Friday? I show you we're talking about the Babylonians and the circle and the hexagon inside the circle. Did we talk about that a little bit? Okay. So that's where the 0 to 360 degrees came from. If you missed that discussion, it should be online. You can go back and watch that. But talking about a radian, here's what a radian is. Okay, this is the best explanation I've ever seen for this. So we'll pause this and jump back and forth. But that right there is going to be a radius for our circle. Okay, so we're going to take our circle and we're going to start tracing out. Now, wherever I stop that, if I look at where my cursor is, I look at that right there, and then this segment here, together they'd be an angle. Does that make sense? Okay. I'll keep playing this out. Okay, so every angle that you talk about is going to be some portion of a circle. Okay, starting from the center and then taking maybe another ray here. So that angle there would be a portion of 360 degrees, correct? Does that make sense? Okay. What a radian does, or is that we take that radius And we're going to take it outside, and we'll keep it right there. So that radius we initially saw, which would have been right there, whatever units that is, if it's 1, 2, 3, whatever, okay, inches, feet, miles, if that was, let's say, 10 feet, this here is 10 feet. Does that make sense to everybody? Now what we do is we're going to take that 10 feet and we're going to bend it. Okay? So if you're walking from those two red points, from one of those points to the other, you've walked 10 feet. The same distance, it's just curved around the circle. Does that make sense? Okay? Now what we do to talk about what a radian is that we take that angle right there. And that angle is equivalent to 1 radian. The word radian refers to radius. Does that make sense? And we took the radius and we bent that around the circle. Okay? No matter how big your circle is, okay? No matter how big your circle is, when you take that radius, so let me see if I can, now this is going to be terrible because I can't draw circles, or do I have a, I don't have a circle tool on here. Let's see if I can draw a rough sketch of a circle here. Not great. But if I were to take that radius right there and wrap it around right there on that circle, okay, it still ends up being the same green angle, doesn't it? Okay? So no matter how large or small my circle is, 1 radian is always the same. And it's the same idea for an angle in terms of degrees. 1 degree, no matter how big my circle is, it's going to be 1 degree. Okay? But now, here's where this becomes real natural and real useful. When we take that radian and basically do the process again, so cut and paste, now we've got 2 radians. Make sense? Cut and paste, I've got 3 radians. Okay? Now, I want to fill in, you kind of see this little sliver right here, right? I want to fill that in. And what I end up filling that in with is 0.14. Okay? It's like 14129, whatever. And eventually I get that half a circle right there to be pi radians. Does that make sense? Okay? So if I were to go all the way around, when all the way around, we get 2 pi radians. Does that make sense? So 1 complete revolution around the circle is 2 pi radians. Well, what do I get when I take 2 pi times my radius? What's 2 pi r the same as? What's that an equation for 2 pi r, or formula? Okay, so 2 times 3.14 times my radius is equal to what for a circle? Here, it's the other one. Circumference, right? Okay, so 2 pi r, or 2 pi times my radius, is the circumference of my circle. So that relationship makes it a little bit nicer for us to work with radians, with circles and angles, than it does degrees. Okay? What we find out, if we kind of replay this again, we end up getting out there to a point where we had, what, 3.14 radians, so pi radians. And right there is pi radians. Okay? How many degrees would that be? If I look at that green angle that's being traced out there, how many degrees is that? 180. There's a conversion factor right there. If I want to go back and forth between radians and degrees, okay, 180 degrees is equal to pi radians. Okay? That's terrible. It looks great on my screen. 180 degrees is equal to pi radians. Okay? So if I divide that, if you take 180 degrees divided by pi, I'm doing my calculator, I don't know this number, it's like 57 something. 180 divided by pi, 57.29. Okay, 57.29. So what that means is 1 radian is equal to about 57.2 degrees, or 57.3 degrees. All right? Much like how we convert kilometers into miles. Anybody know how we convert from distances in different units? You guys know that 1 inch is equal to 2.54 centimeters. And that allows us to go from our English system of inches to our metric system of centimeters, okay? Which then allows me to go from miles to kilometers eventually as well. But those are conversion factors. This will be something, guys, we're not going to spend a whole lot of time right now talking about radians because of our comfort level with it. We'll spend a lot with degrees. But once we start to work in degrees and understand our processes, we'll come back to radians and use that a little bit because the end of course exam might ask you questions about it. It has asked you questions about it in the past. Okay? If you ever look at your calculator, you guys have handheld calculators? Get your handheld calculator out. I'm specifically kind of talking now. The big TIA 384 is this way as well. But if you've got a calculator like this, there should be on there a button right next to your second key that says DRG. And as you push that, it gives you an option, DEG, RAD, or GRD. The DEG stands for degrees, the RAD stands for radians, right? When we work with our calculators, we're going to have an understanding of which one of those we're supposed to be in eventually, okay? When we work with something like Desmos, okay? We're going to have you see how I can toggle back and forth between RAD and DEG. I'm going to have to know which one of those I'm in, okay? It's basically a built-in conversion of pi equals 180, okay? And I have to be able to make sure I go back and forth between those two options correctly. So that's something to kind of put in the back of our minds. There are two different units for measuring an angle, degrees and radians, okay? In regards to using degrees, these are the way that we categorize our angles, okay? This should be stuff that is old information. You guys should know this stuff from previous years, okay? Acute angle 0 to 90, not including 0 and 90. If I have an angle that's 0 degrees, that means the two rays that are the sides of my angle are on top of one another, and I do not have an angle. Does that make sense? It's like taking the clock, which the hands on a clock form an angle, right? If it's 12 o'clock, both of those, the minute hand and hour hand, are on top of each other, right? So there is no angle being created when it's 12 o'clock. Okay? If it's 90 degrees, then we get, obviously, our right angle. Okay? So an acute angle cannot be 90 and a right angle be 90 at the same time. These things are called mutually exclusive. They cannot happen at the same time. Obtuse is greater than 90 but less than 180. And that's just something we're going to focus on right now. We'll eventually talk about an angle that's 210 degrees, 230 degrees, that kind of thing. But right now we're focusing on 90 to 180 being obtuse, and not including 90 and not including 180. And this one is maybe one that maybe you've never seen written this way, a straight angle. What's a straight angle look like? Doesn't it look just like a line? Or opposite rays. Okay, now they're going to use straight angle because it makes more sense in some of the upcoming vocabulary to use the phrase straight angle as we define other objects. Makes more sense to use that than it does to say line or opposite rays. So a straight angle is just an angle that has a measurement of 180 degrees. You guys know that stuff already? Okay. The ones with the right angle in them. Okay. And this is very critical for us as we move on throughout the year. Looks like a right angle, correct? Okay, but I don't know that until I put a protractor on top of it, or I have some vocabulary that tells me that those lines are maybe perpendicular, or some other work that shows me that is indeed 90 degrees. Okay? Because that angle that I just drew freehand might actually be like 89.99999 degrees. And if it's 89.99999 degrees, it's going to fall in that category, isn't it? It's going to be acute. Okay? Or it might be 90.0001 degrees, and therefore fall in the obtuse category. When we have inequalities like these, when I say 0 is less than x is less than 90, that does not mean that 1 is the first value you look at and 89 being the last one you look at. Does that make sense to everybody? Okay. When I see 0 is less than x is less than 90, okay, that is implying, now I'm not going to be able to write this, this is why we have to write this way, but it's kind of implying that we've got an angle that could be 0.0, I'm going to repeat that number forever, and then stick a 1 after it. That would be kind of the first angle that needs to be included in here. Does that make sense? And then the last angle that I would include would be 89.9, and I probably should put equality on these, but that would be the last angle that's included in that. Does that make sense? And obviously those are not really good ways of writing an inequality, so we use the less than symbols, 0 and 90, and those less than symbols mean we don't include those. I want you to understand, though, when we use inequalities, a lot of people do this, they want to think the first number that's involved there is 1. It's not. Okay, it's 0.00000 forever, and then a 1. Does that make sense? A lot of people want to leave out fractions and decimals and all that kind of stuff in inequalities, and you can't do that. But going through here, I need to be provided information that that's a right angle. So they need to show me that little box there in the corner. Otherwise, I can't make the assumption that it's 90 degrees, even if it looks like it, right? Okay. And we'll talk about making assumptions off of looks a lot in this class. So that's one thing to pay attention to. Okay. Just go ahead and write down this information right here. Okay. Call it the protractor postulate, but then write down this information. And I'm going to, as you're writing that down, I'm going to fix this picture so it makes a little bit more sense as we work on it. Okay, so what the protractor postulate is saying, I'll read it to you, At first, it sounds like just a bunch of mumble jumble, and that's what a lot of our postulates and statements are going to sound like the first time we read it. But once we break it down sentence by sentence and kind of construct a picture with it, hopefully it's a very simple concept that we can kind of agree to exist. Let's consider ray OB. Okay? So up there, we're talking about this ray, O to B. Okay? Now, I'm also, and this way this postulate's written from this textbook doesn't incorporate this, but if I've got ray OB, there always exists a ray that's opposite to it. So I'm going to draw this ray OC. How many degrees would that angle BOC end up being? If those two things are opposite rays or a straight line, 180 degrees. Okay? What the protractor postulate is saying is that we are essentially going to attach 0 degrees to ray OB. That's the coordinate for ray OB. Ray OC is going to have a coordinate of 180 degrees. And then if I put A on either side of ray OB, so it could be up there up top, or if I wanted to, we could move it we can move A, there we go, down here if we wanted to. It doesn't matter, okay? I'll put it up top just because I got room up there. There then exists a ray that goes from O to A that is going to be paired with some number between 0 and 180. And that pairing sets up a protractor. Think about this. If that's OA, then maybe A could be there where the tip of my cursor is. Does it make sense to everybody? And if that's A, is that going to be paired with a number different than what it was when it was here? And it's going to be between 0 and 180. So no matter where this ray is, each one of these places that I stop, it's going to be paired with a number between 0 and 180. Well, if I were to trace that out, what kind of shape do we kind of get when I trace that out? Do we like a half circle? Okay, if I were able to keep that distance the same. It looks like a half circle. Does it look like, not that. Does it look like that? We've got a protractor here, right? What a protractor is, let me zoom in on this. We've got here, this would be ray OB right here. Okay? This one over here would be ray OC. And then these purple and red ones would be those, any of those rays OA that are between OB and OC in terms of their measurement, 0 to 180 degrees. Does that make sense? All right, so now this allows, so that protractor postulate creates this tool right here. Okay, that setup is our protractor and generated by the protractor postulate. What it allows us to do is measure the span between any two angles. Now, most of the time, and I'm just going to go off of what my experience is when I was in like the 4th grade or 5th grade or whatever grade it was that you first were provided a protractor, but we were taught this. Take your protractor, there's a little hole right there, right? You take that protractor and you place that hole on top of your vertex of your angle, right? And the next thing you were taught was to take your protractor and rotate it so that one of your rays goes through kind of one of those base lines at the bottom, right? Okay, does everybody remember doing this? And then you were to look up here, so it's going through 0 or 180. So then I come up here and I look at this and I track through what is it going through. It's 80. This would be 85, 86, and the next one's that 87, right? And that's how we measure things using a protractor. Okay? Or you rotated it and you put that one on that baseline, and then you came up through here and it's the same game, right? You still find that 87 that one's passing through. You don't have to do it that way, though. You don't even have to put it so that it's horizontal. If I do something like this, let's go try to get that through this one passing through 140. If I got that one pass, and I know it's maybe kind of hard to see here, but that one's passing through 140 degrees. This one over here is passing through, looks approximately 53. Now, there might be a little bit of human error in there and the protractor that I pulled off the internet here. But if I have those two things, if I subtract 140 and 53, what do you get? You get 87. You still get that span between the two rays. All right. It's the same idea we talked about when we measure something with the ruler. You don't have to have one of your starting points being 0 on your ruler and the other one being 50. You could have one starting point being 20 and the other one being 70 and still get the span to be 50 between those two endpoints, right? So it's the same concept here. I get 87. Now, no matter what I do, if I rotate and put this through 10, so that one's going through 10, and you see over here, this one's going through 97. Okay? Well, if one's going through 97, the other one's going through 10, subtract them, and I get 87, right? Okay? Now, why do we use that in the 5th grade, 6th grade, or whatever? Isn't it easy to subtract 0 from whatever I find that red ray going through? So that's why you do that in those grades, because you're subtracting 0 away, and maybe we don't have an understanding at that point of this formula right here. But basically, this is the same thing as our distance formula. It says the measure of an angle COD is the absolute value of the difference of the real numbers paired with OC and OD. So basically, it's the coordinates of your two rays. You subtract them, and you take the absolute value. Same exact procedure you use with the ruler, right? And my hope is that we start to see these connections, the things that we do with our rulers and segments, and the same thing we do with our protractors and our angles. Okay, same exact formula. So what's going to happen on I'm never going to have you work with a protractor in class, okay? Even this is kind of a stretch for us in regards to using this GeoGebra. What I'm going to do on tests and quizzes is give you a picture that looks something like this. Okay, so we got a bunch of angles up there, right? A bunch of different rays that we can use. And I'll ask you, find the angle measurement for angle FAB. FAB. And you would find out what F goes through, AF. You would find out what AB goes through, and you would find the difference in those two. Does that make sense? So I'm like, in that picture, I could ask you, there's a lot of different angles up there that I could ask you about, okay? Maybe I want to find the angle HAB, okay? So it looks like H is going through, or AH is going through 100 degrees, and AB looks like it's going through about 134. So HAB would be about a 34-degree angle. Does that kind of make sense? Or sorry, 134 degree angle. Can we do that? That's pretty straightforward. All right. So because we have that, because we have the protractor postulate, we can then talk about congruent angles. Okay, and here, all I want to talk about here is that when I talk about congruent angles, notation-wise, if I say like angle ABC is congruent to angle XYZ, remember that idea is that a shape on shape idea. Okay, the two shapes are landing on top of each other. They're cut and paste images of one another. If they are congruent, then, so they do land on top of each other, that means their span or their angle measurement has to be equal. And remember, this means a number equals a number. So a specific example of this, maybe measure of angle ABC is 45 degrees. Then what would that tell me measure of angle XYZ is? Also 45 degrees. And we see there's our number equal to now or nothing. Okay, so those two things in notation, we approach them a little bit differently, right? A, B, C, congruent to X, Y, Z, encapsulates not only the same shape, but same measurement. This just tells me two numbers are equal. Okay? And that gets us to the last slide. Okay, so we'll just do one example. Last class thought that this was enough to get an understanding what's going on because of what we do with segment addition. Tomorrow, we come in and we didn't do so well in this angle addition stuff. We need more examples. We can do that. Got it? But it says the angle addition postulate is set exactly the same way the segment addition was. If you remember, segment addition said you had points A, B, and C with B on the interior of A and C, or between A and C, right? Here it says you've got B on the interior of angle AOC. So it gives us some point on the inside of an angle. Okay, very similar structure to the segment addition postulate. It is then saying if that's the case, you can then draw ray OB, and that's going to take your overall angle AOC and divide it into two smaller angles, right? You can take those two smaller angles, and because they're right next to each other like this, we'll talk about what the word is for them being right next to each other tomorrow. A measure of angle AOB, okay, that yellow one in the picture, plus the measure of angle BOC, the blue one, should end up giving me the total angle AOC, which would be that purple one there. That kind of makes sense? Okay. All we are talking about, and these two ideas, segment addition and angle addition, are going to be very, very influential in all the other things that we do. Okay? All it's saying is if you've got these smaller parts, you can add them up and get the total, right? All they're saying. Okay? If I look at this one down here on the bottom, okay, it's asking us to find these two things. But if I look at my picture, would everybody agree that I've got that angle right there? Angle RQS. I'm going to write measure of angle RQS. Do I also have that purple angle right next to it? SQT. I'm going to add that, so plus measure angle SQT. Would you all agree that if I add those two together, I'm going to get that overall angle, RQT? A lot of times I like to color code things, but I think visually it makes a little bit more sense to see it that way. So here we had that orange angle, which is 4x minus 20 when I substitute. The purple angle, when I substitute, that was 3x plus 14. It's angle addition, so that's going to be a plus sign between them. Is equal to RQT. Now RQT, it's not in the graphic, right? It's not in the picture. What is RQT? 155. Okay? So a lot of times, one of your components is going to come from the direction. And now, hopefully, we can solve that. We get, what, 7x's? Minus 6 equals 155. Add 6 to both sides. How many times does 7 go into 16? Twice, right? Now give me 14. So that 16 is going to change to a 2. So now I'm left with 21. How many times does 7 go into 21? 3 times, right? Okay, so 161 divided by 7 is 23. Is that what they asked? They asked me to find out? I need to find measure of angle RQS and the measure of angle TQS. So RQS is 4 times 23 minus 20. And TQS is 3 times 23 plus 14. When you evaluate those, what's 4 times 23? It's 92, right? 92 remove 20 is 72. What's 3 times 23? 69 plus 14? 83? Okay. What do I get when I add those two numbers together? 155. Which tells me that I've done things correctly, right? When you do these problems, and in segment addition as well, on tests, quizzes, homework, you should know when you submit a test or a quiz whether you got these questions right or wrong before you submit, because you can always go back in and check them by adding those quantities back up and see if I can replicate that 155. We'll stop there. Like I said, there's 2 more examples there if you guys want to go through those. If you go through those on your own, I've got the solution to those. You can have those tomorrow. All my PowerPoints are going to be that way. I don't know if I've said this before. I'm going to make more example problems than what we have time to go through. Okay? If you're a person that wants to do those example problems or needs to do those example problems on their own, by all means, do them. Then come see me and I can give you the solution for it. Okay? There is an assignment 1.4 in Math Excel. We'll go over those tomorrow. Any questions you have on that? And then we'll start talking about angle pairs tomorrow.